Hi guys, my name is Albert and this is my channel Einbert Electric. Today I will discuss a very important topic which is entitled Single Motor Branch Circuit Complete Design Calculations. This is still part of the electrical fundamentals for the design, installation, and maintenance of electrical systems. Now let us see what are the requirements in designing a branch circuit. So what are the things that we will design? So we will concentrate particularly on branch circuit. Number one, conductors. Conductors is very important since this is the one that connects the power supply and the load. So we need to design for these conductors. Number two, overcurrent protection, or for the motor it is called short circuit and ground fault protection. Number three, disconnecting means or isolator. In some cases or in many cases we have to consider the disconnecting means or an isolator. Is it required or not required? Depends on the requirement of the installation. Number four, we have to consider the controller, if the loads are motors or if the load is a motor. And number five, we need to design the overload protection. This is again mostly for motor loads. Now let us see how the motor feeder and branch circuit looks like, so we will have a clear understanding what are we going to do in each of these components of the circuit. So we have given a motor. This is actually a three-phase motor which I have taken from site. This is our feeder, and connected to the feeder is a short circuit and ground fault protection. In this case, this is a circuit breaker. And also we have the branch circuit conductors and equipment grounding conductor. Also we have the disconnecting means, and we have the controller, and inside this controller we have the overload device. Also I have included here for just for an overview, a thermal protection device. Thermal protection device is internal of the motor, and usually it is designed and installed during the manufacturing process. So we will not include the thermal protection device in this branch circuit design calculations. So now let us discuss about conductors. So what are the things to be considered in designing conductors? So number one, we have to know the correct ampacity. So how are we going to do that? In designing the ampacity, our source is the code rules. So we will find how ampacity will be sized or will be designed. Number two, we have to know the appropriate insulation. We have to decide. So this depends on the application. For example, if your motor load will be installed outdoor in a damp location or in a wet location, so you have to decide what type of insulation. Number three, conductor physical protection. This is again also depends on the application. So here, what are the protection that we are going to apply to protect our conductor? Here we will consider the raceway, what type of raceway or conduit, or is it will be installed in a cable tray or cable ladder, etc. So this depends also on the application. Voltage drop consideration. For voltage drop, since this is a motor, we have to consider the voltage drop. And this is dependent on the length of run. So if the motor is very far from your source, then we have to consider the voltage drop consideration. But as a general rule, even if the motor is very near to the power supply, during the design, we have to provide the voltage drop calculation. Site installation and environmental conditions. So, in designing conductors, we have to consider the site installation and environmental conditions. We have to know what is the temperature on site. Is it always raining? Will it be installed in an snowy part of the world, or are you installing it in the desert, or will the conductor be exposed to extreme temperatures? So that we have to consider so that we can size properly the conductors. Number 6, short circuit thermal withstand. This is very important for the motor because, as we all know, motors are contributing to the short circuit current. So, by the rule, a motor larger than equal or larger than 50 horsepower, we have to consider or calculate the short circuit thermal withstand of the conductor, because during fault conditions, the motor will contribute to the fault current. This is a very complicated calculation, so we will consider it in another lecture topic episode. Now let us go to conductor opacity code rules. According to NEC, section 430.22, single motor. So it is telling how to size the conductor for a single motor. It tells that single motor used in a continuous duty application shall have an opacity of not less than 125% of the motor full load current rating as determined by 430.6A1 or not less than specified in 430.22A through G. So this is the next section, opacity and motor rating determination. A, general motor application, and 1, table values. This is the code rule. Other than for motors built for low speeds, less than 1200 RPM, or high torques, and for multi-speed motors, the values given in 430.247, table 430.248, table 430.249, and table 430.250 shall be used to determine the opacity of conductors, or ampere rating of switches, branch circuit, short circuit, and ground for protection, instead of the actual current rating marked on the motor nameplate. So this code rule is simply telling that if the load is a motor, we have to use these tables to get the full load current of the motor, and we should not use the current rating as placed in the nameplate. Also, it is telling if the motor is marked in amperes and not in horsepower, the rating shall be assumed to be that corresponding to the value given in these tables and interpolated if necessary. So if the ampere rating only is given for the motor and horsepower is not given, and the value is not directly found in the table, we have to do the interpolation. Okay, now let us see the FLC tables. This is given by the NEC, National Electrical Code. The first table is table 430.248. This is the table for the full load currents in amperes of single phase alternating current motors. So we can see here the horsepower rating and the voltage rating. So whatever is the voltage rating and the horsepower, we can check that full load current of the motor. Same thing here in table 430.249. This is the full load current for the two-phase alternating current motors. And table 430.250, this is the full load current or FLC of the three-phase alternating current motors. So for motors, when calculating the conductor, we have to use these tables, not the nameplate. So this is shown here, the FLC of the motors. We shall call this FLC. We will have a convention that if we are going to take the values from the tables, we will call it FLC or full load current code from tables. Motor nameplate details. So this is the given nameplate of the motor. This is a three-phase motor, 30 kilowatt, 380 volts for the delta connection, and 60 amperes. Also power factor is given 0.84. So let us see how we are going to work on this nameplate details. Just take note of this nameplate details. So this 60 ampere, we will call it as FLA. So the first one is FLC. The current value we have taken from the code and from the table. Here we will call it FLA. The current rating we have taken actual. A means actual or from nameplate. Okay, so take note, there are two. FLC means full load current code table, and FLA is full load amperes actual from nameplate. Okay, so let us see how we are going to design the conductors. We are given motor nameplate 30 kilowatt, 380 volts, 60 ampere, and power factor 0.84. These are the given details. From National Electrical Code or NEC 2017, table 430.250, there is no column for 380 or 400 volts to get the FLC of this motor. But from another code, which is the Philippine Electrical Code, also 2017, table 4.30.14.4. There are current values for FLC for the motors. What it is given, 51 ampere corresponds to 30 horsepower and 66 ampere for 40 horsepower. But our load motor is given in kilowatts. So how are we going to deal with this? What is the right thing to do if the motor data doesn't show the horsepower rating? As per the code, we have to do the interpolation if only current is given in the nameplate. However, here 30 kilowatt is given, which is equal to 30 kilowatt times 1 horsepower over 0.746 kilowatt. This is actually equivalent to 40.2 horsepower. So this 30 kilowatt is the mechanical output. It was only expressed in kilowatt. So this motor is actually 40 horsepower motor. So from the table, in the Philippine Electrical Code, we can get the value of the 40 horsepower and 400 volts or 380 volt. It is 66 amperes. Therefore, we shall use 66 amperes for our conductor calculation. So current for the conductor opacity, so we use 66 ampere and as per the code 1.25. So the resulting value is 82.5 amperes. As per the code, this is the minimum value of conductor opacity. Note that if the equipment terminals has a marked terminal temperature rating such as 60 degrees centigrade or 75 degrees centigrade, conductors must be sized on that equipment terminal temperature rating if there is no marked terminal temperature rating on the equipment. See section 110.14 on electrical connections. This is found in NEC section 110.14, and we shall apply this. So take note that we have also to consider the equipment terminal temperature rating. Otherwise, we will not get the proper calculation for the conductor opacity. Now let's just assume that a motor terminal temperature rating is 75 degrees centigrade. If terminal temperature rating is not marked, so if there is no marking, we have to use 60 degree centigrade. So from the table when you see in 75 degree column, if you have to see the table, which also I showed in my first video lecture episode, I showed how to use this table, so you can get back to that video episode. Conductor size is number 4 with 85 ampere opacity. Also, comparing from the table of Philippine Electrical Code PEC, in the 75 degree column, conductor size is number 4 also, equivalent to 22 square mm with the same 85 ampere opacity. So coincidence that they have the same opacity. Now for the conductor size, we will call it as option A. Remember in my first video lecture episode, In calculating the branch circuit conductor size, we have two options. Which one is greater? That conductor size will be the correct one. So option A. So as option A, use 3 by number 4 American Y gauge or 22 mm squared, either THW or THHN, stranded copper conductor with 85 ampere ampacity. If you are going to see the table, this is exactly the same in 75 degrees centigrade and 90 degrees centigrade. Also note that this conductor doesn't consider, number 1, the rung length of conductor. So this calculation is not considering yet the voltage drop. I will discuss separately a voltage drop which is directly related to this calculation in another video lecture episode. So also watch out for that one. Number 2, the site installation, like ambient temperature and type of installation. So this employs correction and adjustment factors. So how the cable will be installed and what are the environmental conditions in the place where the conductors will be installed, we have to consider that. But here in this calculation, it is not yet considered to simplify our conductor calculation. Number 3, the current contribution in case of short circuit. So this is also not considered because this will be considered during the short circuit calculations. Short circuit thermal withstand of this conductor should be considered in the final sizing of the conductors. So that means this conductor sizing is not yet final because we have not yet considered the short circuit calculations. Now let us go to option B. As per the code, National Electrical Code, assumptions. So let us assume again and the actual conditions on site of installations. So in the site of installation for the conductor, the ambient temperature reaches 38 degrees centigrade and the conductors in a raceway or cable. So there are 3 conductors since they are 3-phase. So there are 3 conductors. And if we are going to see the table, which is also I showed in the video lecture episode number 1, the temperature correction factor from the table for 38 degrees, it is 0.82. And for the adjustment factor, this is 1.0 or 100%. Why? Because the cable, the conductors is not more than 3. So it is 1.0. The factor is 1.0. Now let us calculate the total derating factor. So 0.82 times 1.0, that is equal to 0.82. This total derating factor, we have to multiply this factor to the probable ampacity values in the conductor table that will retain the motor rated current of 66 ampere as in the FLC table. So from the conductor table, we have to randomly select an ampacity and multiply it with 0.82, our total derating factor. So whatever is the value that will retain this 66 ampere FLC of the motor, that corresponding conductor size we have to consider. Okay, Then we will compare it to option A. Whichever is larger, that conductor we are going to use. Now, this is the table 310.15b16. This is the conductor table. Now, a 75-degree mark on the motor terminals. Same as in option A. So, in option B, we will also consider the same 75-degree terminals. So, we have to use the 75-degree column. So, for 85 ampere opacity on the 75-degree column, I of the conductor, 85 ampere times 0.82. This comes out to be 69.7 ampere. So this is the effective opacity, and it is more than enough to carry the rated motor current of 66 ampere. So we have effective opacity of conductor in the 75-degree column, 85 ampere times 0.82, we have 69.7. This is more than enough for the 66 ampere full load current. Now, this is also equivalent or corresponding to number 4. As you can see, this is number 4 American wire gauge. So the same conductor size as we calculated in option A. So we don't have any problem to select. We have the same conductor size, number 4 in option A, and now in option B also. So we have confirmed that this is the conductor size, number 4 or 22 mm squared. Now let us see the circuit design summary so that we will have a clear view in our mind. Motor nameplate 30 kilowatt, 380 volts, 60 ampere, 3 phase, power factor 0.84. This is our feeder and conductors. So we have selected now for the conductor size, use 3 by number 4 American wire gauge or 22 mm squared. Either TSW or THSN, stranded copper conductor with 85 ampere opacity. So other things will be there, but we have not yet calculated. So these are pending to be calculated. We have the short circuit and ground fault protection, equipment grounding conductor, disconnect switch, controller size or capacity, the range of the overload device, the setting of the overload device. So now we have calculated only the conductor size because this episode is only for conductor size. Okay, so what's next? Because the lecture episode number 2 is about short circuit and ground fault protection calculation. So we will know how to calculate the circuit breaker. We have done for the conductor. So thank you very much for listening. Thank you very much for watching. This is again my YouTube channel, Einbert Electric. If you like my video episode, just click like, click subscribe, and click also the notification bell and select all, so you will not miss any of my new video lecture episodes. Thank you and God bless.